Hello and welcome to this course on MATLAB programming for numerical computations. We are in week 11 of this course. In this week, we are discussing partial differential equations and numerical methods to solve them. In the previous couple of videos, we have talked about method of lines, which is a powerful technique to solve transient PDEs. In the third lecture of this week, we have talked about method of lines to solve parabolic PDEs, and in the previous lecture, we talked about method of lines to solve hyperbolic and first order PDEs. In this particular video, we are going to talk about solution using finite difference approach in order to solve PDEs. Okay. This is more for academic and student interest. This is because in a typical numerical methods course, we do teach finite difference approach to solve PDEs. Okay. However, when it comes to computational techniques, because we have more powerful approaches to solve these PDEs, we do not need to resort to finite difference approach. However, it is still a good tool to try to learn, and therefore, I am including this as bonus video. You can very well skip this video without missing any of the information required for solving PDEs using MATLAB. So, without further ado, let us talk about solution using finite difference. Let us talk about parabolic PDEs. Okay. So, parabolic PDEs, what did we say? Let us say we have this rod and we are going to have this rod into n intervals. Okay. So, we will have I equal to 1, 2, 3 and so on up to n plus 1. Our step size, we will call this as h. Okay. Now, so at time t equal to 0, we will have these initial conditions. At so instead of calling t, let me call it as k equal to 0, at k equal to 1, we will have these values again at location 1, 2, 3, so on at n plus 1, and we will repeat this for as much time as we want. Okay. Let's call this discretization as delta t. Okay. And let us say and ith location. Okay. So, we are going to use forward in time, central in space. Why central in space? Because central in space is second order accurate method. Okay. So, dt by dt at any time I, sorry, any location I and time k is nothing but at ith location divided by delta t. Okay. What we have over on the right hand side is exactly what we did 2 lectures earlier. So, we will just do this, we will have Ti okay, this is what we have. Okay. Because this is forward in time, the t's are going to be used at time k. Okay. If this was backward in time, then these guys we would have just used at k and k minus 1 instead of k plus 1 and k. Okay. And this is basically what there is to it. So, we can have Ti and this is what you get. Now, what's the very nice thing about an explicit method like this is you don't have to solve any equation over here at all. Okay, you have the values of all the temperatures at time k, and you just substitute them into an expression of this sort and you will get temperatures at time k plus 1. So, you start at 0, you go at 1, 2, 3, 4, 5 and so on up to your end point, and you will be able to solve this problem without any issue. Now, there are two problems with this. One is the step size, the maximum step size delta t that you can take depends on the step size h, that is the spatial step size, as well as it depends on the value alpha. Okay. For a lot of problems of practical interest, the value of delta t that you need to take is really small for stability. Okay. Now, there is one more problem, is this method is only first order accurate in time. Okay. So, it is not a very stable method and it is first order accurate in time, and those are the two main issues with parabolic PDEs solving using FTCS method, forward in time, central in space. Okay. If you look at this particular approach, okay, and you compare it with what we did in the third video of this week, okay, what we are doing is in the third video we use method of lines to convert the PDE into ODE. Okay. Once you get the ODE, if you were to use Euler's forward difference approach, that ODE will get converted into this particular expressions. Okay. That is all there is to solving the parabolic PDEs using forward in time, central in space approach. Okay. I will demonstrate that using the hyperbolic PDE example, so that you can see how this particular method can be derived from what we talked in the previous video and what we talked in week number 7. Okay. So, what we did in previous video for hyperbolic PDE is we said d theta by dt at location I is going to be nothing but negative u okay. If okay, so this is what we have. So, we can substitute this and rearrange. So, we will get theta I okay. This is what we are going to get, sorry, k multiplied by delta t. Okay. And we take this on to the other side, minus theta I we are just going to take on the other side, and this is the expression that you can get. Okay. So, what we have done in the last few minutes is we looked at parabolic PDEs and hyperbolic PDEs. The parabolic PDEs we derived it using the textbook approach. So, any numerical method textbook uses this forward in space forward in time, central in space approach in order to discretize both in time and space. Okay. Alternatively, the same thing you could have done by first discretizing in space resulting in ODE, and then discretizing the ODE in time, so that you will get forward in time, backward in space method. Okay. So, this particular method that I have shown you over here has a very interesting name. It is called an upwind method. Okay. Why it is called an upwind method is if u is positive, okay, you are going to use backward difference formula, but if u is negative, we are going to use the forward difference formula instead. Okay, that's the reason why it's called upwind method. Okay, this comes from the fact that this method originated in aerospace engineering. So if, or as well as in physics of course, but as the wind is flowing in this direction, you need to take ith location and I minus 1's location in the direction opposite to the wind flow. If velocity was negative or u was negative and wind was flowing in this direction, then you have to take I plus 1 and I, okay, in the direction opposite to wind flow, I and I plus 1 in the direction opposite to wind flow. So that's the reason why it's called upwind method. Again, this is a very small tidbit of information for you, so that you can understand where the original derivation of these particular techniques came from. Okay. Now, with that, let us talk about a higher order accurate method, and the higher order accurate and more stable method is what is called as Crank-Nicholson. Okay. And the idea of Crank-Nicholson is very simple. It borrows from the midpoint method that we talked about in week number 7, okay, with a slight modification. In the Runge-Kutta second order midpoint method, it was an explicit method. The Crank-Nicholson method uses a semi-implicit method. What I mean by that is, we will write d theta by dt as nothing but okay, but f we are going to calculate it as this is how we are going to calculate. Okay. So, this okay. So, this is another approach in order to solve partial differential equations. Okay. This again I am including this for the sake of completeness. Now, the Crank-Nicholson method is second order accurate method both in time and also in space. Okay. As a result, it's both more accurate as well as it's generally more stable. Okay. So, with that I come to the end of this lecture. In this lecture, we have talked about a couple of general approaches that we teach in a typical undergraduate course. This lecture was a bonus lecture. This was meant for sake of completeness, so that you can understand the things that you are taught in an undergraduate numerical methods course. Okay. With that, I come to the end of this lecture. Thanks for watching. Bye.